So let's start the second talk of the day. So we welcome Romain Demelle. He's from Université de Poitiers, and he's going to talk about K3 surfaces limiting action of M20.
Yes, thank you. So I would like to thank the organizer to allow me to give a talk today. And before I start, I just want to mention that this is a joint work. So joint work with Paola Comparin. Okay, so first I will start with an introduction to fix some idea. Introduction. So a definition, a K3 surface is a compact, complex, in our case, smooth surface such that it's simply connected. X is simply connected, and it admits nowhere vanishing to form, which I call omega x. Okay, and for the rest of this talk, we'll consider X will be a K3, a projective K3 surface. Okay, so now consider a finite group G, which is in the automorphisms of X. And these groups act on X. Okay, and this group G induces an action on the vector space H20X, which is C omega x. Okay, and this action is for all G in this group, G star omega x is equal to alpha G omega x with alpha G some root of the unity. And alpha will be a map from G to C star. Okay, and with this, we get an exact sequence which is this G0 G Z over MZ 1. Okay, and here we have the map alpha that we defined before, and this group is up, and maybe okay, nice. And this group G0, which is the kernel of alpha, is the group that we called symplectic automorphisms. So G0 is the group of symplectic automorphisms. And it means that the automorphisms in G0 acts as the identity on omega x. G star omega x equal omega x. Okay, and this group here in the exact sequence is the group of non-symplectic automorphisms. We called non-symplectic automorphisms. Okay, So we have three important results. Three important results, which are the following. So first, Mukai studied such groups G0 acting symplectically on X, and he described 11 maximal groups. Okay, Shao in 1986, he gave a complete list. Of such groups, and there are 81 such groups. And finally, last result, Kondo in 1989, he showed that the group here, G, has order less than this, 3,840. Okay, and it is an interesting question to know the K3 surfaces admitting such action, such a symplectic action of this group G0. So we know that when G0 has order maximal, which is 960, then G0 is isomorphic to the Mathieu group M20. Okay, so we will suppose for the rest of this talk that we have this. Just a remark before I continue. Oh, sorry. So when the big group G has order maximal, so no, it's a 40. Okay. So it is 4 times the order of M20. There exists only one K3 that admit such an action of M20, and this so one K3, which is a Kermer surface when G is equal to this, so it is 2 times the order of M20. There are 2 K3, okay, which admit such action of G0. So these K3 are, we call this X-mu for Mukai, and it lives in P3, and X Ronders Tashimoto, which lives in P5. Okay, so the first surface is just defined by a quartic, and the second surface is defined by an intersection of 3 quadrics. So they are both a complete intersection. Okay. And we show with Paola, so theorem, combine. We showed that there exists, when we suppose that G has order 916, we showed that there exists an infinite number of K3 surfaces admitting such action of M20. So it is a big result, because when when the group G0 is strictly included in G, there is only 3 surfaces admitting such action. But when we suppose that G is the master group, then we have an infinity of K3 surfaces. And the aim will be now to study this K3 and maybe construct a projective model for all this K3, give some general properties, etc. So there are any questions here? If there are not, I will continue. And I will continue with lattice theory. We'll need a little of lattice theory to understand how classify the K3. So remember that for a K3 surface X, we have that this cohomology group is equal to 3 times U 3 times plus E8 minus 1 2 times, which is called usually the K3 lattice. K3 lattice. Okay. This is the hyperbolic plane, and this is the lattice associated to the E8 root system. Okay, so this lattice has good properties such that it has rank 22, it is even, unimodular, and the signature equal to 390. Okay, so now we consider the pK group of X, which I denote pkx. So let pkx be the pK group of X, which is the group of divisors modulo linear equivalence. Sorry, and we denote by Tx the orthogonal complement of the pK group in the K3 lattice. Okay, and it is called transcendental lattice. Okay, this lattice will be very, very useful for what follow. And just to remark, thanks to the true form omega x, one can show, this is not hard to show, but I don't know if I have the time. One can show that Tx is included in H2xz, M20. So this is basically the K3 lattice invariant by the action of M20. And this inclusion implies also that the pK group contain the orthogonal of this. Okay, and this lattice was computed by Kondo, and he computed that H2xz M20 is isomorphic to L20, and L20 is a rank 3 lattice, which is explicitly this. -2, -2, -2, 12. Okay, so as I said, this rank is 3. It is a positive definite. 3, 0. And it has a discriminant equal to this. Okay, and I will don't write it here, but we know the isometries of this lattice. Okay, and we know that, so yeah, I will write it. The isometry of L20 is spanned by -2 identity, ρ1 and so ρ1, which is a permutation, and ρ2, which is this. Okay, and remark that in these conditions, we have necessarily that the picker number of X, so rho X, which is the rank of the Picard group, is necessarily bigger than 19. And as 20 is the maximum possible, we have this. And actually, we know that the Picard number is exactly equal to 20, and the K3 surfaces in this case are called singular K3. Singular K3. Okay, and just the last thing, we can observe that the surface X, oh, sorry, the surface X contains a M20 invariant ample class that we call L, and such that L square is equal to 4n with n a positive integer. Okay, so just it is quite natural to have this square because L is in L20, and for all V in L20, the square of V is a multiple of 4. Okay, and as we have this class, we can remark that X, which is projective, we suppose it projective, X is in P2n plus 1. Okay, and why we do all this thing? This is because all the singular K3 surfaces, so all the K3s that have a picker number equal to 20 are classified in terms of their transcendental lattice. So singular K3 are classified in terms of their transcendental lattice. And in our case, we know that the rank of Tx is 2. It is an even lattice and it has signature 2, 0. So it has this form 2a, b, b, 2c with a, b, c some integers. And as I said before, for all v in L20, the square of v is in 4z. So it implies that, oh, okay. It implies that Tx has, in fact, this particular form in the case where X is a K3 surface admitting an action of M20. Okay, and this is all for the lattice theory. I will talk now about the projective model. Of X. So one of the main goals is to describe the embedding for n in L20, where for n is this, with L square equal to 4n. And we study this lattice in order to study the existence of the K3 surface for any value of n. And actually, studying this embedding will allow us to compute the transcendental lattice, so to compute Tx, or not. If the embedding doesn't exist, we will not compute it. So to do this, we denote by EFH, standard basis of L20. So basically, this is just the basis given in this matrix. So E square equal to 4, etc., etc. And we look for some integers lambda mu delta such that L is equal, so it is not a real equality, but I will write it as this. And we have, we want lambda equal to lambda E plus mu F plus delta H. Okay, and that is to compute this integers lambda mu delta. We take the square of this equation, and we have L square, which is equal to 4n, is equal to this, 2 lambda minus delta square plus 2 mu minus delta square plus 10 delta square. Okay, and I will denote this equation by star. So just an example before I continue. Example, we suppose that L square is equal to 12. So we are in the case where n is equal to 3. So why this case? Because the two first case, L square equal 4 and 8, were already studied, and we know the projective model for those two cases. And L square equal 12 is the first case which admits faithful and symplectic action of the Mathieu group M20. So in this case, by solving the equation star, we obtain 8 possibilities for the integers lambda mu delta, and these 8 possibilities are all in the same orbit under the action of the isometry groups. 8 possibilities which are in the same orbit. So we can suppose, before we made the computations, L equal to H. And when we have this, we can compute the transcendental lattice Tx. So we don't do all the computation, but just the ideas. We know that Tx is equal to ZL perp in L20, sorry. So we compute lambda 0, mu 0, delta 0, some integers, such that the product of this mu 0 f plus delta 0 h with L is equal to 0. Okay. With this, we obtain two vectors, u1 and u2, that span the transcendental lattice Tx. And in this case, we obtain that Tx is equal to this. Which is associated to a unique singular K3 surface. And this is the first example where the surface is not a complete intersection, okay? Because we'll see it later, but we can see that the surface X in this case is defined by quadrics, only quadrics, and it is defined by 10 quadrics. So this is not a complete intersection. Okay, so this is the end of the example, and we continue with a proposition, and it is an interesting question to know when the equation star, which is here, admits a solution. And we know that the equation star admits a solution if and only if n is different from this integer. Okay, I don't have the time to prove it, but it is not hard to prove. Just the idea. It comes from a result of Romain, which say that an even positive integer can be expressed as this if and only if so 2n, if and only if n is different from this. Okay, so we can put some lambda mu delta, which depends on x, y, and z, and we just have to check that it is a solution for the equation star, and they are all integers, but it is not hard to prove it. Okay, so an example of a case which have no solution, L square equal to 24 is the first case without solution. So we are not able to construct the transcendental lattice in this case. And a remark, when the embedding, when the K3 exists, the embedding is not unique in general. And an interesting example is L square equal to 20. This is the first example where we have two distinct embeddings, we can compute two distinct embeddings 20 in L20, and we compute the same transcendental lattice in each case. In the two cases, we obtain the same transcendental lattice, so the same case resurface. Okay, we don't know yet why we have this phenomenon, but
sorry, Romain.
Sorry. Yeah. Yes.
Could you please finish in like 2 minutes?
Yes. Yes. 2 minutes is good for me. So okay. Just a last proposition, a last result we obtained with Paola about the projective model. So first, the linear system L is not hyperelliptic. Oh, sorry, is not hyperelliptic, which means that the morphism from X to the projective space given by Hill as degree 1. The surface X is only defined by quadrics. And we exactly know the number of these quadrics. The number of quadrics is exactly this. Okay. And I will finish here. Thank you for your attention.
Okay. Thank you for your talk, Romain. Let's thank the speaker. So any comments, questions for Romain? Well, if not, let's just thank the speaker again.
Thank you.